Okay, here we go. So today we're going to talk about perpendicular lines. You may or may not remember perpendicular lines, but in pre-algebra, you were introduced to these things called perpendicular lines. We're going to get three theorems out of this. Last couple classes, we talked about special angle pairs. Remember, those are two angles that share some sort of relationship with one another. And we have many of them this year in geometry. The ones that we talked about are only one set, and that was adjacent angles. Adjacent angles share a vertex and a common side. Last class, we were introduced to three more relationships when you have two angles. The first one was complementary angles. Two angles added up to 90. They could be adjacent. They don't have to be adjacent. Supplementary angles, two angles that add up to 180. They could be adjacent. They don't have to be adjacent. And then the last one was vertical angles. Remember, angles that are opposite one another when you make this X formed by either segments, rays, or lines. Okay, today we're going to get one more, and those are perpendicular lines. So this is another shape that you will get a pair of angles that have a special relationship. So it should be a quick and easy class. So we'll just start off by the definition. If you have two lines that intersect at right angles or that form a right angle, then by definition, we call them perpendicular lines. And if they are perpendicular, you put that little square to indicate that angle is 90 degrees. Okay. We also have a symbol to show that lines are perpendicular. So let's see, I have line AB and line CD, and that upside down T is the symbol for perpendicular. Remember, perpendicular can apply to lines, rays, segments, or any combination. All right, so let's do a proof. So let's see, what am I trying to prove? I'm trying to prove that if you have perpendicular lines, that all four of those angles are congruent. So let's see how that's done. Let's think this through. There's many different ways you could do this particular proof, and it doesn't really matter the starting step, but there's probably two statements that you could make about this. We'll start with the first one. And the first one is because of the given. So if you notice right here in the given, right here, it states that line L and line N are perpendicular. Remember, this is the other way of writing um, the name of a line. We can pick 2 points, or we can use a lowercase italicized letter. So line L and line N are perpendicular. So by the definition you just wrote down, they form a 90-degree angle. So one of those four angles is 90 degrees. Let's just pick one. So I'll just pick angle one. So by the definition of perpendicular lines, the measure of angle one is equal to 90. Okay? I said there were two things, so there's one thing. And the other obvious thing is that, well, the very last thing we did in the last class was talk about vertical angles. Well, angle one is vertical to angle three, so therefore they must be congruent by the definition or by the theorem 2.3 vertical angles are congruent. Okay, now we're kind of stuck. So we've shown that one and three are the same or congruent. I need to show that one is congruent to the other ones. So let's think this through. Well, the last thing you could probably say if you stared longly at the picture is the following, and that is if you notice that there's a straight line that's formed right here. So let's see, what would that mean? That would mean 1 plus 4 is equal to 180, or 1 plus 2. I could have stated it either way. I chose 1 plus 4. All right, well, that's true. That's just the definition of supplementary angles. 1 plus 4 make a straight line. So therefore, they must equal 180. And oh, look at that statement just two above this. We said that 1 is equal to 90. So if 1 is equal to 90, then I could plug in 90 right there and then subtract 90 from both sides. And now the measure of angle 4 is 90. So let's see. Um, Let me do this in red. What do we have now? Well, we have the following. We have that 1 is 90. 1 is the same as 3, so therefore 3 is 90. And now we just said 4 was 90. We're only missing 1, and that's the measure of angle 2. And can you see how we're going to get that one? Yeah, look at 2 and 4. 2 and 4 are vertical to one another, so therefore they are congruent. And now we have shown that all the angles are congruent because they're all equal to 90, right? So the definition of congruent angles are angles with the same measurements. We show that they are all either congruent or they were equal to 90. And that's a theorem, right? And the theorem is 2.4, which states if two lines are perpendicular, they form congruent adjacent angles. And you're like, well, what about the verticalness of them? Well, yeah, 1 and 3 are vertical, 2 and 4 are vertical, but we're going to say this as adjacent angles. 1 and 2, 1 and 4, or 2 and 3, 2 and 1, 3 and 4, or 3 and 2. So any adjacent angles on perpendicular lines end up being congruent. So that's the if and the then. Now, there's two consequences there, notice in yellow. One is that the angles are congruent, and by the definition of congruency, if the angles are congruent, then their measurements are equal. You could remember this as either one. Now, the statement itself in theorem 2.4 states that they are adjacent and congruent. All right, so if we think about all the consequences of being perpendicular lines, let's see. Consequence number one, the angles form 90 degrees. If any one of the four angles in that particular shape right there, that X is 90, well, then they're all 90. And then lastly, perpendicular can be, the term perpendicular can be used with line segments, rays, planes, or any combination. A plane could be perpendicular to a line, or a ray can be perpendicular to a segment, so forth and so on. Cool? All right. So that was theorem 2.4. What do you think about the converse? Let's see, what would be the converse? Remember, the converse is given an if-then statement, then we flip-flop the if and the then. So let's see, what would it say? If two lines form congruent adjacent angles, then they're perpendicular. And the question is that true? And the answer is it is. This is actually a proof in exercise 2, so I'm not going to prove it in class, but you can probably figure this one out. So let's see, I'll give you a hint. So let's see, what's the if part? If two lines form congruent adjacent angles. So if the adjacent angles are congruent, that means they're equal to each other. If they're equal to each other and they're supplementary, in the case of 1 and 2, then they must add up to 180. Therefore, you could solve that and get a 90, and that's how you're going to prove that they are perpendicular. Oops, I just gave you the proof. All right, so that's theorem 2.5, the converse to it. As a side note, we just proved that the conditional was true and the converse was true. So technically, this is an if and only if statement. Our book chooses not to write it as a biconditional, but it is. All right, another idea. So we have what's called a talking proof, and I kind of just did one. I didn't fully do the proof, but I gave you a hint, and that's where I simply talk you through the proof. Maybe I'll draw a diagram, but a talking proof is one where you just talk through it. You don't actually do a two-column proof. So here we go. Think about this. If I have an angle, right, there's an angle right there. And I cut that angle, not necessarily in half. I'm not bisecting that one, but I am forming two adjacent angles. So I start with this right here, and then I draw another ray through the vertex, and now I've made two adjacent angles, angle one and angle two. What would be the consequence if we had started by saying the original angle was 90? I'll go back one time. So we start with an angle. We form two adjacent angles. They're definitely not congruent there, but they're adjacent. And the original angle was 90. What's the consequence of that? And the consequence is that, well, 1 and 2 are adjacent. And since they form a larger 90-degree angle, then 1 plus 2 must equal 90. And that's the definition of a complementary angle or complementary angles. So therefore, the consequence is that they are complementary. So this is theorem 2.6. And it says it kind of strangely. It doesn't talk about the angle. It says if the exterior sides, one side, two sides, of two adjacent acute angles are perpendicular, which what they're saying here is that OA and OC are perpendicular, hence that's little square right there. Then the two angles formed by that must be complementary, and that's how it's stated. Okay. Well, that was three quick theorems. Right? Proof of this one, you're going to do an exercise number 13. This will be the last time that you have I call them proofs with training wheels, where you're filling in the blanks. Starting in the next section, you're going to be doing the proofs all by yourself. You got to fill in everything. And I actually find it at this point that these fill in the blank proofs are actually harder than when you have to do one all by yourself. Because when you're doing it all by yourself, no one's forcing you to make a statement. You kind of come up with a statement yourself. Whereas these fill in the blank ones, you got to see what the person is thinking rather than you doing the thinking. So what just happened? We talked about three theorems. They all involve perpendicular lines. The first one stated that if two lines are perpendicular, or two rays, or two segments, or two planes, or a combination of those, if they are perpendicular, then they form a right angle. We also proved the converse to that as well, too. So if two lines are perpendicular, all four angles are equal to 90. They form adjacent complementary, adjacent supplementary angles as well too. And then the converse is true. So those two things. And then we had our last construction, which is when you have the exterior sides of two adjacent acute angles, that's OA and OC, if they are perpendicular to one another, then they form two adjacent complementary angles. Cool. I need to show you something, right? When you're doing your homework, you notice there on the left there, problem number two, and then problem number three. Problem number three is in color. Whenever you see color, they are implying that that's in three dimensions. So if you think about that, whatever that color right there is, yellow, green, whatever it is the surface of your desk. Then OZ is a stick that's coming out straight from the center of your desk. That ray OZ, that's a stick sticking straight up. So three is in three dimension and two is only in two dimensions. Lastly, and I always get questions on this, our book loves tables, right? It loves giving you problems with tables. So let's see this table. First off, we're told that these two ray in this line are perpendicular and these two rays are perpendicular. And then it gives you a number and it says angle CBF is 40. So if we trace out CBF, we're told that this is 40. I'm writing with my finger and my mouse, so this is a little bit challenging. Okay, so that's 40. And then you have then you have um, one, two, three, and four angles that they ask you questions about. So let's see, EBF. So I'll do this in blue. So here is angle EBF. So it is adjacent to angle that measures 40 degrees. And how in the heck am I going to figure that one out? Well, if we go back to the given, we're told that BE, so this one right here is perpendicular to this one right here. So that means this forms 90 degrees. And if one of them is 40, well, then the other one has to be 50. 90 minus 40 is 50. So that's how that one is done. And you can do the rest yourself for practice. And the more challenging one is the one where they give you the X. And the first time you see this, you're unsure of what they want you to do. Well, they just want you to do the same thing. Well, if this is X, we figured out that this was perpendicular to this. So to figure out this angle right here, you simply take 90 and subtract the given angle, and the given angle is X. So not a very satisfying answer. You want a number, and in this case, you get a variable expression, 90 minus X, but that's the answer. And like I said, our book loves to do these tables. You see this in nearly every single section and every single chapter that you'll get these tables. And it follows a similar pattern where they give you one question where they give you numbers, and then eventually they just give you a variable or a variable expression and ask you to fill in the rest of the answers. Okay, this one's straightforward here. Oh, let me go back to that. This one's asking you to justify a statement. So I don't know, let's pick number 8 right here. So it says if RS is perpendicular, so if RS is perpendicular to TV, then Y is 8 congruent to 7. Well, 8 is congruent to 7 because perpendicular lines form two adjacent angles that are supplementary to each other. So that's what they're asking you to do, justify. You can justify it with a statement, You can justify it with a theorem or a definition. Any of those would be justifications for it. Make sense? Okay, I think that's it. Is that it? Let's see. Yep, that's it. All right, so there's your homework. Good luck with it, and I'll see you in the next video.